Alright, welcome back to chapter 19. It's a long chapter, right? Let's go ahead and finish it up though by looking at these last few sections, and then I have a lot of practice problems for you to work, and most of that you can do on your own, but it'll help you understand these concepts that we're looking at. Here we're going to talk about conjugate addition. You may remember the word conjugated from an earlier chapter. It's kind of related to that. And specifically, we're going to talk about addition to alpha, beta, unsaturated aldehydes and ketones. Okay, and I'll explain what that means as well. So we'll get a firm graph of everything that matters. This turns out to be a very important synthetic procedure, meaning this is the way that we can build up really sophisticated molecules in organic chemistry. So that's pretty much what I'm telling you there in this second bullet. It allows for building up of alpha, beta, unsaturated carbonyl compounds. Okay, and all that really is an alpha, beta, unsaturated carbonyl compound is you have a carbonyl, okay, and we got some carbons over here, so on and so forth, but we have a double bond there, right? So henceforth, this is called alpha, and this is called beta. So it's an alpha-beta unsaturated carbonyl compound. We use the word unsaturated, we're making reference to having double bond there. So that's a generic structure. Alright, didn't have to do that because here it is in the box. So if I use the word alpha-beta unsaturated carbonyl species, then you know what I'm talking about. Now, it's a pretty busy term. We can also call these enones, right? This is known as an enone, an example of an enone. But what's the point what's the big deal here? With a carbon labeled beta, in other words, this one is highly electrophilic, okay? Highly electrophilic for reasons you'll see when we draw the resonance forms. And therefore what? Nucleophiles can attack there. But it can attack at any of the two positions. Which one? Well, the exact nature of the nucleophile, okay, will determine which carbon is actually attacked. So we'll talk about exactly where the nucleophile will go. But let's look at these resonance forms. Okay, so here's the one that you're kind of most used to, right? It mimics that one. If I were to take this pair of electrons here, okay, and just place it there, then we would have that resonance form, right? Now this is not a very major resonance form because that carbon doesn't have an octet. This would be a minor contributor. This is a minor contributor. But it doesn't allow you to see how a nucleophile would want to go here because it's plus charge. If on the other hand, okay, how about we change things up a little bit? In addition to moving that pair of electrons onto there, how about at the same time I place this pi bond here, then we would have this form, okay? And folks, this is a major contributor. Major contributor. And then you can say, well, which one's in the majors? Is that the major one, or is this a major one? Actually, this one. Okay, this is the dominant resonance form, and you probably would not have guessed that back when you were taking Organic 1. Okay, so here you are. You're a nucleophile. You are a nucleophile. Okay? And what do nucleophiles do? They seek out nuclei. Well, where would this one go? It would go there. And what did we call that carbon a while ago? We called it the beta carbon, okay, with the alpha. So that explains what's going on in this box. The nucleophile is going to attack the beta carbon. All right. So here's a couple bullet points. We've seen that nucleophiles attack the carbonyl carbon already. We've seen that a lot, right? When we did the Grignard reaction, when we did the sodium borohydride reduction, when we did the imine formation, the enamine formation, the acetal formation, the list went on and on. Everything was attacking the carbonyl carbon. But if you've got a double bond, between alpha and beta, okay, it's going to attack the beta carbon. So this is 1, 2, and 1, 4. That's just simply the atoms. If I were to number the atoms 1, 2, 3, 4, I can do that. Let me do it over here, and I'll use blue. Let's call that one 1, let's call that 2, let's call that 3, let's call that 4. So the attack is taking place at carbon 4, and the charge, okay, is being influenced over here, oxygen 1. Now there's 3 fundamental versions of this, okay, and I'm going to walk you through all 3. 3 fundamental versions of conjugate addition. It's kind of easy to understand. You just have to get a grasp of what's going on. Folks, this is an example of a pure addition. Don't lose sight of that word addition. Okay, that means you're adding 2 molecules together to produce 1. In other words, this is compound A on the left, this is compound B on the right, and this is compound C as a product. Okay, A plus B gives you C. Now, without going through a detailed mechanism, you can probably tell what's happening, or we can look at a mechanism as far as you want to look. When you were forming imines and enamines, this nitrogen, right, was attacking there. Okay, but it's not going to happen in this case because we have a double bond. This carbon here instead is very, very electrophilic. So let's put the lone pair on that nitrogen, okay, and show that attack taking place right there. All right, let's do that. Because again, that carbon, that's the beta carbon, and it's very, very electrophilic. Now when that happens, this pair of electrons can be displaced onto the alpha carbon, and we'll draw that intermediate here in a second. I think this mechanism should be intuitive to you by now. Hopefully it is. If not, just look over it again. And if you're wondering, could I speed this reaction up by adding a little acid, catalytic amount of acid, like we did before? You sure can. Certainly can. So here, I want to make these in different colors so you can see how all this is happening. I'll put this in green. There's that nitrogen that you formed the covalent linkage with. Okay, and this nitrogen possesses 2 hydrogens and a methyl group. And because of that, it also bears a plus charge. All right. Now keep in mind, we haven't finished this illustration yet, but there was a hydrogen there all along, right? Okay, and there was a hydrogen here all along. And that carbonyl just kind of did its thing, and the carbonyl influences the reaction because it's it pulls electron density away from this carbon there, and now our negative charge is right there. Can you see where we're going? What has to happen next? Simply put, all that has to happen is for this lone pair to pick up that proton, which it can. It's perfectly positioned to do that intramolecularly or intermolecularly, and this pair of electrons will collapse towards nitrogen, and henceforth, this is how we generate this compound that you see on the right. So this was a conjugate addition of an amine to, in this case, an alpha beta unsaturated ketone. Call this a Michael addition. Named after R.B. Michael, a famous English organic chemist. Let's go to page 140 and look at the other types, and we'll do some practice, and we're pretty close to finishing this chapter actually. Conjugate addition of alkyl groups using organocopper reactions. Now you've seen those before too. These would react with acid chlorides to produce ketones, and they can actually displace halogens. But as you might guess, they can actually attack beta carbon. So generally speaking, here's your alpha, here's your beta, and here's our organolithium species. All right, let's go ahead and draw that out. And this is R. Now R can be simple things like alkyl groups, but they can also be aromatic rings. They're not restricted, okay? You're not restricted to aliphatic R groups. and it would go there. Now it's a little more complicated than what I've shown. This copper would coordinate to that oxygen in this pi system to make this bizarre looking complex. But I'm showing you the overall result. It's simply the transfer, okay, of this entire motif to the beta carbon. And then this pair of electrons could reside on the alpha carbon, and henceforth you quench it, and you quench it provides a proton there. So the R group was installed by step 1, the conjugate addition of the organocopper reaction. The proton was installed in step 2 by adding acid. So this is the general example. Here's a specific example. Okay, so if you'll follow the line of reasoning for this one is for that one, then you'll be in good shape in terms of understanding that. So in this case, we're adding a methyl group in the form of methide to the beta carbon, and we're protonating the alpha carbon in step 2. So in terms of bookkeeping, let's just do that. I'm going to highlight those things so you know where they came from. How did that methyl or that methide get in there? From step 1, right? Came from step 1. And how did that proton get on that alpha carbon? From step 2. Okay? By adding a Bronsted-Lowry acid. Okay, now again, your job is to do what? Is to carry out some of these on your own. So you have to recognize when you see this, okay, you're looking at what? Diphenyl copper lithium. Okay, that's an organocopper compound. We call those Gilman reagents. We also call them cuprates. We look over here, we say, okay, there's a carbonyl. Is it going to go here? No, it's going to go there. Okay, so I'm going to label these alpha and beta respectively. And what is pH? That's a phenyl ring. Okay, that's a monosubstituted benzene. So probably the best way to solve this kind of problem is to draw everything out like you see on the left. But leave out the pi bond because you're going to replace that with certain atoms. Okay, so I'm just basically drawing everything that I see there on the right. Okay. And then it's incumbent upon me to recognize what happened in step 1. In step 1, I added whatever's inside here, okay, to the beta carbon. That's the beta carbon. So that means what? That means we now have a phenyl ring here. I'm just going to use the letters pH. And it also means that in step 2, that we're simply going to protonate that. Okay? So my illustration here is a little bit sloppy, okay, but I think you get the point. In step 1, we added an aromatic ring, a phenyl ring here. In step 2, we put a proton there, so the double bond is gone. The important thing is to remember that the nucleophile went to the beta carbon and the proton went to the alpha carbon. So I have a few bullet points. You're not responsible for knowing how to prepare organocopper compounds. In other words, you don't need to know how to make these. Okay, it's not that hard to do, but you don't need to know that. But you are responsible for predicting. Okay, so we're going to do that in the next problem. In other words, what if this were an empty box? Okay, and you were given that. I would want you to be able to fill that box in. Okay, in other words, here's another example. What if this were an empty box and you were given that product? Could you fill that box in? And it's real simple. You just identify the R group, whatever it is. Okay, in this case it's methyl. Remember, there's always going to be 2 of them bonded to copper, but you make that into a salt by placing a lithium there on the right hand side. So let's do another problem here. Okay, this is getting close to the end of chapter 19. It says provide syntheses for the following compounds using conjugate addition reactions. Okay, all right. Okay, so we kind of have to look at these and go, okay, all right. Here's my carbonyl, which means this must be the alpha and that must mean the beta. And if I'm really busy about it, I can say, well, I know there's hydrogens on there like that. Okay, somehow or another, though, I need to get the species where I attach an ethyl group at the beta carbon. So if I had a species that I could begin with, that had a double bond between alpha and beta, I could install that group using the process that we just learned above. So how about we begin with the following ketone, okay? In other words, cyclopentanone. And now, whoa, put that double bond in there, right? So it's cyclopentenone. I think we're good to go. Just think about what we've done. Here's your alpha carbon. There's your beta carbon, right? Now, it's not necessary to do this, but you can sketch the hydrogens in just to, remind you or remind ourselves that there was one hydrogen already there and there's another hydrogen here, but we need a third one, and those are going to come from what we put on our reaction arrow. All right, so step one, we need a source of ethyl groups. So there's ethyl. Remember, there's two of them, copper, lithium. Now, technically, when you do this reaction, you do need an ethereal solvent. So we're going to use diethyl ether. Now, if you forget that, no big concern, but in the lab setting, it wouldn't work without the ether. The ether makes it form a complex, and so the complex exchange becomes very integral to actually getting one of these R groups to transfer to the beta carbon. Now, step two, use any kind of acid you want. It could even be water, but let's just go with our generic hydronium ion, okay? And that could be dilute hydrochloric acid or dilute sulfuric acid, even water, as long as it's a source of a Bronsted-Lowry proton. Now, the second example, the thing that you should spot right away, okay, here, is that that's an amine, okay? And this is the nitrogen that has two R groups, right? Both are ethyl, so that means you're going to use a secondary amine. And so I think it's pretty smart to do kind of like we did before. Let's go ahead and sketch in a hydrogen here and a hydrogen there, okay? There's alpha, there's beta. We don't need to do all this, but just to kind of reinforce how this is all taking place, which means I need to go ahead and, kind of like the previous problem, produce this 5-membered ring, cyclopentanone ring, but I need a double bond here, and I see that there's a methyl group already there. Okay, so whatever's already there needs to be there in the organic component. There's a hydrogen. Okay, so we're getting closer. Now, unlike the previous problem, this is a pure addition reaction. Okay, in other words, we don't have to quench this reaction. We're adding A plus B. So the thing is, what is B? B is manifest, okay, the simplest way. I'm going to draw this two ways. Is by sketching those ethyl groups like this. And remember this proton here? Well, that proton there is actually originally found on that nitrogen. So this would be compound A. This is compound B. And this produces compound C. This is an addition reaction. Now, if you wanted to represent that amine, this, by the way, is called N,N-diethylamine, or if you just want to call it diethylamine, you could have done it this way as well. Okay, I don't mind if you condense this down. Like that. Either way is fine. But there you can see, probably a little easier to see that and that together. So these are conjugate addition reactions. We call it conjugate addition because the nucleophile attacked, okay, the beta carbon of this conjugated system, okay, because this carbon is very electrophilic. Nucleophiles are not going to attack alpha. They're not. They're only going to attack beta. Unless it's a Grignard reagent, which I'm going to allude to in the next page. All right. Folks, you really want to get it ready for exam 4. In other words, you say, I want to know those reactions so well that they're going to become instinctive. What I'd like you to do is to cover up, okay, all the answers here, cover up all these, and on a sheet of paper, see if you can figure out the products, okay, by reacting all of these different species, A, B, C, all the way to I, with carbone. You'll notice that carbone is has ketone functionality. It also has an enone. It's an alpha beta unsaturated species. It's a very interesting compound to look at when you want to discuss the reactions that we've talked about in the chapter. And so down here in the lower portion of page 141, we have all our answers. So cover up the answers, okay, and see if you can figure out the structures without actually, peeking first. And if you can do that, then you will have mastered essentially all the reactions in this particular chapter. So this whole page here, this whole page that you're looking at, page 141, is a review. All right, let me write that in. This is a review. Is that how you spell review, like that? Yeah, it's a review. So look over that to make sure that you understand what's going on. Okay? So I would like to say one thing in particular. If you'll look at B, right? If you look at reagent B, folks, that's a Grignard, right? Grignard reagent. You recognize it. It's phenylmagnesium bromide. Now, Grignard reagents, they don't attack beta carbons. They don't attack here. They're always going to attack carbonyl carbons. Now, there is a way, chemically speaking, to modify them so that they will attack carbonyls, but we're not going to talk about that. Okay? So that is the one that I wanted to emphasize, that here you do not get 1,4 addition, you get the 1,2 addition reaction when you use a Grignard. It doesn't attack beta carbon, it only attacks the carbonyl carbon. So look over this as a review, okay, and you'll be in good shape for exam 4. Now, you need more review, don't you? Folks, on page 142, this problem took forever for me to come up with. So please, please promise me that you'll do it, okay? And this will help you understand, again, all the reactions, particularly the reagents that are necessary here to carry out these functions. So this one actually starts here, keeps going left to right, left to right, left to right, and until we get all the way to this final product that you see in the lower right hand corner. Okay. Now this is a tough problem. Some of them are pretty easy, some of the steps, but honestly, if you'll spend the time figuring out what reagents go on these arrows, then you will have totally mastered this entire chapter, okay? I promise you will have mastered this whole chapter. Now, when you do that, it's very tempting to peek, but don't. Try to work it. Keep working. Go back in your notes. Go to your book. Go to OWL, whatever you got to do. Don't peek. But when it comes time to look, I have the answers on page 143, okay? In other words, these are the reagents on the arrows that are needed to carry out these organic transformations so that you can get to this very simple species there to this very complex species here. Okay, so this is the key to that sample problem on page 142. So promise me, though, you're going to do the right thing. Okay, you're not going to just look at this as a study source. You're going to look at this to compare your answers to mine. Okay, we've come to essentially the end of this chapter, and what I have here looks like I need to get refocused. Okay, sorry about that. Let me put the autofocus lock so that that doesn't happen again. So these are synthesis problems, okay, and your job is to figure out, how do I go from here to here? Okay, in other words, what are the steps needed in order for me to transform that to that? Now, synthesis problems are different than mechanisms. You're not asked for curved arrows or anything like that here. Instead, you have to provide the covalent intermediates and the reagents necessary to carry out these functions. Okay? So let me kind of work a couple of these with you, and then later again you can peek at the answers I've provided. But you always have to, think a little bit outside the box and ask yourself, okay, what's the big difference between what I'm starting with versus what I'm ending with? And if you contrast, the starting material that you see on the left, which is a primary alcohol, Okay, let me just write that in. It helps to make marks like this too. It's the primary alcohol. To the product over there, and I'm going to sketch a hydrogen in here. I don't need to do that, but I'm doing it anyway. It tells us, you know, we're going to make a secondary alcohol. You say, well, is there a way to do that? There's no way to do this directly, but I need to install that group. Okay, somehow or another, I need to get that group on there. Now, there's no way that you can just yank that hydrogen off and replace it with an isopropyl group. That can't be done. You're going to have to go through a series of organic transformations in order for this to happen. But do y'all remember how to make a secondary alcohol? How did we do that? We did that using what? Well, one of the ways we did it was by using Grignard reactions, okay? In other words, a reaction of a Grignard reagent with a secondary, with an aldehyde, would give us a secondary alcohol, right? Okay, so let's think about doing this in reverse. What if I had this substrate? Okay, all this that you're looking at on the left-hand side is just part of the molecule. It's not going to be involved directly. But what if we had this aldehyde? Okay, it becomes an easy problem now, doesn't it? Yeah, you know that you can add a Grignard reagent to this. And your choice of Grignard reagent is dictated by that R group. So you need isopropyl magnesium bromide. So how do we write that on the page? Now isopropyl, when we write it in condensed form, is that, right? Okay, there's your isopropyl. There's your isopropyl group. And you have metal in the middle and you have bromine on the end. And typically we have an ethereal solvent like tetrahydrofuran. That would make this into an alkoxide, and then you would quench it with acid. You can just write the word acid, hydronium ion. You're kind of used to seeing ammonium chloride, okay, aqueous ammonium chloride for that. But that would affect this transformation. Well, then how do we go from a primary alcohol to an aldehyde? Oh, that was easy. Okay, I'm going to draw an arrow like this because we're going to write down two ways to do this. We only need one way, but let's go ahead and write down both of them. One way that we learned was what? The Dez-Martin per iodinane. You can just write in Dez-Martin per iodinane. And that was done with dichloromethane. Or, what was the other one? Remember? PCC and dichloromethane. Pyridinium chlorochromate can affect the conversion of primary alcohol into this intermediate aldehyde. Okay, so this is a synthesis. Notice there's no curved arrows here. We're only providing reaction arrows. On only reaction arrow, we're writing what reagents are needed. Okay, here you can do that one or that one, but you don't need to do both. We're showing the covalent intermediate. So, folks, everything that I've done here is exactly what the directions said. We have all the reagents and all the covalent intermediates. Okay? All right. So that's a synthesis problem. Now, the next problem is there's more than one way to do it. Probably have to think back to your chapter 16 when we were learning about Friedel-Crafts. But let's go ahead and think about this product, okay? What kind of product is that? In other words, I look at that and I go, well, I know what this is. This is a tertiary alcohol. Okay? And I see that, you know, the aromatic ring's there, but I need to get some carbons on there. Okay? Well, what if this, on the first hand was something like a ketone? Well, with tertiary alcohols, and didn't we say we're using Grignard chemistry? There were three ways to make it. We could install a phenyl ring. We could. We could install a phenyl ring to a ketone. We can install a methyl ketone, ethyl, whatever we want to do. There's a whole bunch of ways to do this. But one of several ways would simply be to go ahead and start with, as an intermediate, how about if we had this particular, what if we had this particular ketone? Okay. Now, this could be a methyl for that, or it could be an ethyl for that. Either way you do it, it's going to work. Alright, so there's your ketone, right? And I'm going to write ketone beneath it. You don't have to do that, but just as a reminder. So if we have that ketone, then we would need to install that methide source. Okay, so the best way to do that is using a Grignard reagent. And the Grignard reagent here would be the simplest one there is, methyl magnesium bromide. Okay, and the solvent can be diethyl ether, tetrahydrofuran. Then you've learned that we have to quench it. Okay, we're going to use ammonium chloride, which is a Bronsted-Lowry acid in water. Or you could just write down water, or you could even just write down, okay, H3O plus or something like that. Well, this turns out to be a relatively simple synthesis if you think back to what? Chapter 16. Remember chapter 16? Okay, what did we do if we wanted to install that group, right? We did a Friedel-Crafts acylation. And so you had to figure out what acyl group would go there. And the way that I told you that you could do that would be to write in, okay, the acyl group, this one here. And then what? What do you need? Yeah, it's typically chlorides, okay? You can use bromides as well, or iodides, but just about always your chlorides. But nothing would happen until you did what? What's the last thing you gotta have here? You gotta have a catalyst, multiple choice catalyst, aluminum chloride, okay? So this is sample problem 1922. It involved reactions that you actually learned, okay? This is in chapters, let me see, this is in chapter 16, and this was actually in chapter 17. So it kind of comes together here in chapter 19. So it all kind of builds upon itself. Okay, I'm near the end, guys, and so the next one, sample problem 1923, is going to involve the conjugate addition of amine to this carbonyl. Okay, you can see that, and then you're going to reduce that carbonyl using a reducing agent to convert it to a secondary alcohol. Alright, now sample problem 1924, alright, is going to involve the conjugate addition of a methyl group to this beta carbon, and it's also going to involve the conversion of this ester into this particular alpha hydroxy carboxylic acid. Now, for me to go through this step by step with you would just be very time consuming. So what I've opted to do is go ahead and look at the answers with you and just show you how I went about it. Folks, this was the one that we did on page 144. We already talked about how to do that synthesis. We worked it out. This is the one we also did on the bottom of page 144. Okay, this was the one where you added a Grignard reagent after you did the Friedel-Crafts acylation. This is from page 145. I didn't go through that one. I just talked about it, but let's look at it now. Okay. You say, well, you know what? What's going on here? I need to install a nitrogen way over here to make this particular amino alcohol, but this amino alcohol has the nitrogen very separated, but can I install that via conjugate addition? Yeah. Folks, this is the Michael reaction. Michael reaction. Okay. And that involves conjugate addition of an amine to the beta carbon, this position. So this first step, okay, was simply addition reaction, whereby you install the amine component. I'm going to sketch these hydrogens in the amine component to the beta carbon. Okay, and this would be an intermediate that you could isolate, purify by distillation, however you want to do it. And then the last sequence of reaction implies that you're going to take this ketone, and this is a ketone, and you're going to convert it into what? This would be a secondary alcohol. And how do you do that? Well, the best way is a sodium borohydride reduction, which places the hydride here, okay, followed by an acid quench, replaces the proton there. So that would be a plausible synthesis, really about the only synthesis you could do using the methods that we've learned up to this point. Alright, so this involved 1, 2, you could count that as the third step if you want, but it's really just an acid quench. So these are pretty straightforward syntheses. Now the last one, folks, I'd like you to dwell upon this one a little bit. Again, we're using the chemistry that we learned in this chapter, okay? This is purely from chapter 19 with a plausible answer. But you kind of get a feel for how this works by looking at this framework and comparing it to the final product. Now, if you can work here and go that way all the way to the product, be my guest. But usually you have to kind of work in reverse. Now, the reason I say that is because here we have, okay, this would be alpha hydroxy carboxylic acid that we've come to know these as acetoins, okay, acetoin. This was very early on in the chapter. And the way that I taught you that you can make acetoins is by the hydrolysis of these things, okay, and what are these things called? Cyanohydrins. Cyanohydrin. Now, what's a cyanohydrin? It has a cyano group and an OH group. Okay? So, if we treat this with acid in a process called hydrolysis, under reflux, then we're going to convert that cyano group into this carboxylic acid. Well, how do we make cyanohydrins? Well, the dominant way to do that would be to take what? An aldehyde. So this is our aldehyde. Okay. Treat it with hydrocyanic acid, or sometimes we call that hydrogen cyanide. This is A plus B. Okay, and that gives us this intermediate cyanohydrin. We say, well, how do I get to an aldehyde? Well, we have to do a dibial reduction of an ester. So this particular ester that comes about a result of the previous reaction, okay, let's put a note on here, this is an ester. You can reduce esters to aldehydes using dibial. Diisobutyl aluminum hydride, toluene, at a very low temperature. Now, do y'all remember why that temperature had to be low? Okay. Ask yourself again, why did that temperature need to be so low? It's a very good question to answer. And the reason is to avoid over-reduction of that. Folks, if you didn't have this at minus 78, this would become an alcohol. And then you wouldn't be able to carry out the subsequent reactions. Okay, so dibial reduction reduces esters, okay, to aldehydes. You quench them with acids. Okay, how did this methyl group get installed? Okay, well, one way to install those, which we remember, we have a conjugate addition. This is alpha, and this is beta. The species is conjugated. And so if we want to install a methyl group on a beta carbon, which happens to be very electrophilic, we use the organocopper lithium species. And sometimes it's easy just to call that a Gilman reagent. That's what I like to call them. And that would install that methyl group in the form of methide into the beta carbon. And of course there's two hydrogens on the alpha carbon. One of those gets installed by treatment with acid. Okay? Alright, so this is a very complex synthesis, but it's one that if you look at, hopefully you understand each step along the way. Kind of hard to come up with these on your own, but again, these are the reactions that we discussed in chapter 19. Okay, guys. Okay, that's it. We finished chapter 19. It was just our longest chapter in the book. Okay, and so your exam 4, it'll be about 2/3. Okay, exam 4 will be about 2/3 over chapter 19, and the balance of it will come from our next chapter. So I'll talk to you guys later.